Retrograde, yeah, means like going backwards, turning around, going the other way. Now, before I start, we got to get the credits out of the way. It's a good thing to credit SFU. It's probably a good idea. And this paper here is the one I'll be expositing. So Jalali, Sarebangholi, and Alam. Last year, 2015, as I said, terminal retrograde turn of rolling rings, published in Physical Review E. This is it. Let's hope that my presentation will be a little more interesting than this dry paper. But the author, the lead author, stumbled across this topic when he was just kind of brainstorming and rolling his wedding ring on the table. And it looks something like this. Actually, there's sound. That's good. I think we should see that one more time. Let's try. Okay, watch it carefully. It spins inward, but at some point it goes straight and curves around the other way. Now, just because that doesn't seem as convincing, I actually have here, I have a demo here. So let's try to, I'm going to try to roll this all the way here so most people can see it. Can you guys kind of see it? Yeah, a little bit? All right, so hope this works. We're all familiar with the coin ringing on a spinning on a surface, okay? It follows this sort of floppy trajectory. It spirals inwards. But a ring, on the other hand, while sharing a similar contact point and similar dynamics, watch it. It's doing something similar now. I'll tell you when it gets interesting. Right about here, it starts going straight, and then it bends around the other way. Did you guys see that? Maybe we'll do one more time. It's kind of hard to see from far away, right? Just processing about some orbit here. Now it starts going straight, and it curves around the other way. So if you don't believe me, try this with your wedding ring. And if you're not married, then I'm sure you can get some other ring. All right. Let's keep moving here. So this is the conundrum I'm talking about. When you roll a disc, you get this sort of trajectory. If you track the center of mass, it starts spiraling inward like this and ultimately rattles to a rest. A ring is a little bit different. A ring starts with this prograde spiral, what we call a prograde spiral, and that transitions to a retrograde spiral, flips direction, and it experiences this, what we call a directional walk, and in the middle of that directional walk is an inflection point. So this is a very common behavior in rings that was only picked up, as I said, last year. In order to understand, before that, I just want to mention, this is what the lead author said looking back. He said, all major discoveries of rigid body dynamics had been made in the 18th and 19th centuries, and we thought this is a rare phenomenon that remained unnoticed for decades and maybe centuries. So they're pretty excited, obviously, that their paper got accepted because it's a classical mechanics paper. And it's very rare for this sort of thing to make it into modern journals. So let's take a regression into our classical dynamics class. Here's a closer look at a ring. We're going to define an orthonormal axis that points, it's non-inertial. So it evolves along with the ring as it moves along. You see E3 and E1. E3 points like the contact force from the table. E1 points along the direction of spinning, and E2 points perpendicular to both. It's also interesting to notice, I will need this later, point A is the point above the center of mass C that's on the upper face of the ring. Okay, we're going to need that later. Similarly, we can define three Euler angles in this frame, phi, psi, and theta. Changes in time of those angles give rise to an angular velocity vector that's defined like this. You notice that phi dot, psi dot both contribute to E2. This is because of how we've defined the axes. There's a little bit of mixing between these two, but it turns out to be the most efficient. So let's try to dig back even further to Euler's equations for a rotating reference frame. What it tells us is that the torque gives rise to two effects. In a sense, if you want to transition from a static reference frame here, an inertial frame, to one that's rotating with the system, you get that the torque gives you a spin contribution, that is motion about the center of mass, that's I omega dot, plus something that has to do with motion about the other frame, in this case, the edge of the ring. So Ooh, I is bold because it's a tensor in this case. It acts on the angular velocity vector. Rg cross F, okay, everyone knows R cross F is like a torque. F is the contact force, and Rg is the vector from the edge to the center of mass of the ring. Omega cross Lg, so why is this big omega? Lg is the angular momentum about the edge, and this big omega is just like little omega, except we take away the psi dot part. Actually, that mouse is kind of bothering me. So we take away the psi dot part because that has to do with spinning. So that's already captured in the I omega dot term. Now F, as I said, is the contact force, and it's related through Newton's second law to the acceleration of the center of mass. So mRc double dot is equal to the contact force subtract plus the effect of gravity on the center of mass, which is this one here expressed in the non-inertial frame. Now, in turn, the global position vector of the center of mass, its velocity is related to the angular velocity through the rolling condition, okay? We assume that this ring is rolling, and so there's some relationship between how fast it's spinning and how fast the center of mass moves. That's this condition here. If we take a time derivative of this, we can plug it in for RC double dot. You see that? We'll get two terms. Because of the product rule, we'll get one that goes like omega dot, one that goes like Rg dot. Are you following me? Does that kind of make sense? We get two terms from differentiating this, putting it back in. In turn, we're going to take that and put it all into for F. Okay, so F will get two terms, and this overall contribution will have two terms that look like a triple cross product. Okay, we have Rg cross F, and F has cross products in it. Okay, let's put it all together. So it's not going to be pretty, but this is it. So I omega dot, okay, that's the spin again. I alpha, some of you used alpha for angular acceleration. There's one of the triple cross product terms. The other triple cross product is down there. Big omega cross Lg is just following through. And there's the gravitational contribution at the end. Now, if we want to simulate this system, we're going to take this equation and we're going to multiply. Okay, before I get to that, notice that both of the terms on the left-hand side are acting on the omega dot vector, right? See? Omega dot is on the very right-hand side of both those terms, so we can group both of those into one matrix. The details of this is not too important, but think of it as being one object that acts on omega dot. Now, to simulate this, we act on both sides with the inverse of this matrix M, so that we get an equation for omega dot that we can integrate and get the trajectory. So you see the other terms, there's a gravitational piece and all the others. Okay, so that's exactly what the authors did. Now what happens? This is how it should look. Based on these equations, this is the trajectory that we should get. Now I want you to notice that neither the disk nor the ring follow this trajectory, but the disk is definitely closer. There's certainly no complement with sort of retrograde turn where this inflects and goes the other way. If anything, you can imagine that the disk is following this, but because of some losses, it starts spiraling inward. But there's no resemblance to what the ring does here. All right, can you appreciate that? So, with these dynamics in place, let's take a closer look at how they explored this experimentally. The authors tracked 4 points on the ring's edge using a high-speed CCD camera in order to reconstruct the velocity of point A. Remember, point A that I said is on the upper face in the center. It's just easier to track. This one I actually need to do here. And the directional walk. Pretty neat, eh? Oh, it's so glorious. Okay, now it's turning around the other way. And it ends, keeps rattling, and finishes curving out an S shape like this. The evidence is clear. You've seen the retrograde turn in its full glory. Sorry, the music stops there. So here's some data from the experiment. This isn't particularly interesting to me. We can plot now the horizontal component of that velocity like this. The kind of interesting thing to notice here are these spikes. So these spikes are going to become important later on. There's a very sharp acceleration happening at this stage of the trajectory. So what's the culprit? Why does the ring experience a terminal retrograde turn? This is the obvious question. And one might postulate something like rolling friction. Okay, it's obviously losing energy as it interacts with the surface. Perhaps that leads to slipping. Maybe it's not gripping properly. There's air drag that we've ignored, right? The authors even considered elastic vibrations. That is, modes that get excited in the ring because of its geometry. It sounds a little exotic, but who knows? So it turns out that the ring actually contained trace amounts of uranium. If you don't believe me, just ask Frodo. No, I'm totally kidding, guys. I thought you might like that. It turns out that including only the air drag fully captures the physics of the retrograde turn. This is what the authors have discovered. Now, why do I have two donuts on this slide? And let me ask, what's the difference between these donuts? Anybody? Hands? Somebody? Yeah? This one's got a hole in the middle. Okay, ready? Here we go. Okay, that was a little better. Oh, okay. So yeah, absolutely, one of them has a hole in the middle. So I want you to imagine both of these donuts falling down on their face. Okay, which one's going to be faster to fall? The one with the hole, because air can rush through the hole. Whereas for this one, this Boston cream, air gets cushioned, right? And so it cushions. There's a drag torque, which acts on it and changes that trajectory. The other difference between these donuts that nobody spotted, that this one has equations in the middle. And this is exactly the equation we had previously. And the only difference is that right next to gravity, there's this drag torque. Okay, so the authors said, let's try to fix this. Let's add this drag torque. Now again, in order to simulate this equation now, to integrate it, we multiply both sides with this M inverse. So then we combine this with M inverse to give us this contribution to the angular acceleration. So this is going to be what drag torques do to the equation of motion. And the authors, this is a postulate, by the way. This is a model that they use. They say, we assume that it's proportional to the angular velocity and that it points in the opposite direction. That's kind of what we typically do with friction. We assume it's proportional to velocity and it acts to slow it down with some coefficient. Okay, so it's not going to act on each axis of rotation the same, but it's going to work to reduce those velocities. Just to make sure, I actually emailed the lead author because I was having a hard time understanding this. He says, air escapes through the central hole of the ring and adjusts the resultant drag force and contact frictional force so that the center of mass moves on a retrograde orbit. So there might actually be two effects here. The fact that air is rushing through and causing skin friction, but also that the contact force is modified and the coefficient of friction might change. So how does this compare now to the data? They took initial conditions from the video by measuring initial velocities. Drag coefficients were varied to find the best fit. Okay, that's typical in fitting a model, but the resemblance is actually striking. We notice this is theory and experiment, and there's quite a bit of similarity here, including the number of little cusps it makes before the inflection point. So it's kind of astounding. This now there's of course a drift, and the authors did address this by saying this is probably due to uncertainty in the initial conditions. Okay, and also due to maybe a little bit of slipping at the turning points. I think they're having their cake and eating it too, because previously they said, okay, there's no slipping, but that's what they said in the paper. So we're going to leave it at that. That's why the theory lives a little bit longer. You see. It has a longer trajectory because it's not losing anything. But this is quite impressive. Sorry. Yeah, exactly. Sharper, right? So it's not. It might be slipping, right? So I want to also draw attention to these coefficients that were the best fit. Notice that C1 and C3, which correspond to torques about the diameter of the ring, I would imagine those would be the same. Due to the symmetry of the ring, it seems like those two motions would be objected by the same amount, but it's not so. According to this fit, the best one has those asymmetric. Now we're going to keep the center one the same, C2, because we want to now look at a disk. So to look at the disk, we keep C2 the same, because if you see a disk coming head on and you see a ring coming head on with the same geometry, you can't tell them apart, right? So this coefficient shouldn't change. Now we're going to take the same initial conditions and take these drag coefficients. Center one's the same, okay? The C1 and C3 now are identical, which is what I expected, right? Okay, in this case, they actually do have this symmetry. These are the drag coefficients that best describe a disk. And now look what we get. Boom, the disk trajectory. So this is kind of a sanity check that their model is working not only for rings, but disks. This is a huge accomplishment. And I think the analysis that follows is what got them into this paper. They did a really thorough job of analyzing this, solving the problem. So it turns out that drag torques are kicking the horizontal component of the centripetal contact force, okay? The horizontal component of the centripetal contact force. And that happens every time the ring, as it's rolling, as it's wobbling, when it reaches its lowest point, and then it springs up from that, right? But when it reaches that lowest point, that's when it experiences this kick in the horizontal direction. We'll see that from the data. And eventually these kicks cause the centripetal acceleration to flip sign. So this is the force I'm talking about. It's the component of the contact force which lies along the surface. Now look at red. Red is for a disk. Blue is for a ring from the model. Notice that red, if I, let's put the axis in there. Red is actually slightly increasing as it goes on its trajectory, but it's always staying positive, okay? So the acceleration along, like kind of like centripetal acceleration, always points in the same way. It never flips. But these kicks on the blue curve, they start at the very beginning, okay? You can start seeing the kicks develop at the top from a local minima, and they continue to drive this lower and lower until it actually experiences a flipping point. And that's exactly the inflection point we noticed earlier. So this is a really thorough analysis. And even to take it a little bit further, the authors also observed that the no slipping condition holds, okay? So they actually looked at the friction force, and they looked at how big it can get before they're slipping, and they noticed that this always holds. So mu times the normal force is always greater than the observed frictional force. So slipping cannot be a proper explanation then for this behavior, which is what they initially thought. Maybe the first time you see this problem, you would conclude that it's probably slipping. All right, so we've solved the problem. This is a very exciting time for these authors, and indeed, every time you look at a ring now, you can kind of smile about it. I don't know, at least I do that. Okay, so just some other objects that also might resemble this sort of mechanic. Other objects also experience drag-induced torques. This is not a new thing. So we all know that, okay, this is Sophie Schmidt playing for Canada. Fun fact, okay, I actually took Toastmasters with her. She's pretty cool. When she kicks a soccer ball for a corner kick, it's obviously going to change trajectory, right? If she puts spin on it, it experiences this drag-induced change of direction. And this is an example of drag-induced changes in motion. Okay, one last candy. Does anyone know of a different object which in the air changes direction? Any ideas? Boomerang. Boomerang, do you want another? You already have a candy. Oh, okay, here you go. Okay, the candies aren't working too good. That's my fault though. Yes, a boomerang, perfect. So there's a boomerang in this picture. Yeah, that's because of the drag-induced change of motion, absolutely. This boomerang follows this sort of trajectory, obviously a bit exaggerated. Objects which behave like this are said to be under the influence of gyroscopic precession. Gyroscopic precession. Just like a top, which because of the torque from the tabletop, the contact force, experiences precession in where the angular momentum vector points. This is similar also with, someone else said it, frisbees. So Sorry, it's my last candy. But yeah, the difference with these is that they're not interacting with a surface. They're interacting with the air around them. That also is a little bit different than the ring, because the ring, as we know, interacts with the surface. And as we can see, when you combine these aerodynamic forces with the presence of this asymmetry, this surface beneath it, there's actually very complicated behavior that's experienced. So the ring is a little bit in a category all on its own. Now this has been kind of an enlightening look at a very simple phenomenon, a very household phenomenon, that of a ring spinning on a table. I'd like to just close by a quote from the author where he kind of reflected on the elegance of such a simple problem. He said, "There are many outstanding problems in nature all around us. We do not always need to equip ourselves with advanced facilities to make discoveries and find applications for them. Even a falling leaf can be inspirational." And I would add, wow, what an inspiring discovery. Dr. Herbert. Yes, Darren?
Yeah, so the theory of everything looks really nice when you plot everything. Okay. Compliments to the author. But as an experimentalist, I would like to see that done under vacuum.
That's exactly what I thought. Actually, in my email, I told him that, and yeah, that would be really interesting. It would be a very decisive demonstration that this really is the effect. Of course, he mentioned the difficulty in both spinning the ring and determining initial conditions. So this is, yeah, I think it's doable, but it's going to be tricky. Well, I didn't say that, but definitely, I would like to see that done too. Maybe a thesis project for anybody.
Some equipment is still necessary.
Yeah.
Not necessary, but helpful.
Yes, Nick? Sorry?
Why would you just put it in the
Oh, well, there you go. Now okay. We can make a proposal here. No, honestly, I totally want to see. I didn't think about a glove box. Does that exist?
Yeah.
Don't the gloves like blow up in the vacuum? Like balloons? Okay. Yeah, no, that's totally, yeah, that'd be awesome. Anything else? Yeah, Cheng?
So in one of your slides, you mentioned the sleep returning point. And on the graph, I didn't see that returning point. And how do you determine the location of the returning point?
Yeah. So this is honestly something that bothers me a little bit because they were taking the focus away from slippy forces. So no, we don't want that slide. It's this one, right? Yeah. This is okay.
It's a diagram.
Yeah. Oh no, not the music. Oh, sorry. Yes, there's slippery. What they're noticing is that, okay, and if you remember, I'll go there. I can find it. When we looked at the theory versus the experiment, this one here, yeah, this one's good. Okay, sorry. Yeah, you notice blue, which is theory. It's very sharp. Okay, those turning points are very sharp. But you notice the green one, experiment, they're kind of washed out a bit. And I think that might be due to pivoting. As it's experiencing that turn, it pivots a little bit on that turn, which means the edge isn't infinitely sharp, okay? And is that kind of what you're getting at?
I was thinking about how do you determine the depth numeric value of the turning point?
The coordinates of the turning points?
Yeah.
Oh, so if this was a mathematical theory, this could be described by some sort of a cycloid, is that you're saying? Well, I don't know, and I think not, because this has been numerically integrated. Actually, the cycloid that we saw at the very beginning, which comes from a direct application of Euler's equations, the one that goes like this, actually the authors, they do say that those loops around the edge, They are described mathematically. This is a type of cycloid, some interesting mathematical parametric plot. But yeah, it's a very interesting shape, right?
And what is, if they experiment and compare the trajectory between the ring and the coin.
Yeah.
If it's a coin, that means there's no hole there.
Yeah.
Then you dive the outcome just expect any retrograde motion of the coin.
There isn't. No, that's like the disc I did over here, right? Because a coin is a disc. Now, what I noticed in trying this out with different discs is that there is a little bit of a dependence on the disc geometry. Okay, so I was like, hey, the hula hoop would be perfect for this demonstration, but it doesn't work. It actually just, because what happens is the translational momentum tends to get drowned out very quickly, and so it's not going anywhere. So you can't tell if it's, it just kind of spins in one spot. It doesn't process. So, yeah.
So that's about the thickness of the ring, right?
So the ratio of the height to the width of the ring, yes, does have an importance, I think. You want a ring that's, yeah, and then of course a ring that's a very long ring is not going to work like a pipe. It will just fall over. So there's some dependence here, absolutely. Hello?
I was just wondering what the axis is.
Oh, the axes, yeah, I disregarded those because this is just units. I think what they mentioned is that they normalized the units of this to the radius of the ring, I think. So they say, okay, we're going to take 1 unit equals the radius of the ring, but I don't know if that's accurate. So yeah, they're units of length. This is an XY plot, but I assume that they're arbitrary in this case. That's a good question though, because if you want to take data from an experiment, it obviously comes with some built-in dimensions. Okay, and if you want to scale your theory to that, yeah, so they had to have some metric there.
So we have time for one more question.
This comment that in addition to perform in the vacuum, I also want to perform in the liquid.
Yeah.
That's where the retrograde motion will be obvious.
It will be more pronounced, according to a very heuristic thinking of this. Yeah. In fact, one of the other demos I thought about was having, this is obviously a little impractical, but a tank of water, and just having like a ring and a disc fall through it. Because then you start seeing the ring buffeted due to drag torques, the disc being buffeted due to drag torques, and the ring kind of just slipped through, I think. I didn't actually try it. Or 2 donuts. That works.
Okay, I think we'll have to end it to this. Thank you very much.